Hello, my name is Davis Banger, and let's talk about arc length. Today we will be looking at problem 1 of the 6.5 handout, in which we will find the length of the curve y equals x to the 4th over 4 plus 1 over 8x squared on the interval from 1 to 2. Recall the general formula for arc length of a differentiable curve y equals f of x on the interval from a to b. The length is given by the integral from a to b of the square root of 1 plus the derivative of the function with respect to x squared integrated with respect to x. In our case, a is equal to 1 and b is equal to 2, and a simple calculation shows that the derivative is equal to x cubed minus 1 over 4 x cubed. Thus we have all the information we need to solve this integral. But there are still some algebraic difficulties to solve this integral. It's not an elementary integral in which we know the antiderivative. Before proceeding to solving the integral, let's talk about an algebraic pattern that will be especially useful when discussing arc length problems. We will consider two quantities, a and b, and we will assume that 2ab is equal to a half. So if we look at the expression 1 plus a minus b squared, we can FOIL out the second term. This becomes 1 plus a squared minus 2ab plus b squared. We have assumed that 2ab is equal to a half, so this becomes 1 plus a squared minus half plus b squared. We can combine the 1 and the negative 1 half, and we get a squared plus 1 half plus b squared. We then replace 2ab for 1 half, and we have the expression a squared plus 2ab plus b squared. This is a perfect square and is equal to a plus b squared. This pattern, although seemingly unrelated, occurs in almost every arc length problem, and you should understand and be able to manipulate algebraic quantities in such a fashion. So in our case, we had that dy dx was equal to x cubed minus 1 over 4 x cubed. Now if we let a equals x cubed and b equals 1 over 4x cubed, we can see that 2 times a times b, which is 2 times x cubed times 1 over 4x cubed, is equal to a half. And so the algebraic simplification we will do in the integral at hand exactly mimics the algebraic calculations we made on the previous slide. So we're looking at 1 plus dy dx squared. This is equal to 1 plus x cubed minus 1 over 4 x cubed squared. We expand the second term. And again, we have this 2ab, which is equal to a half. We can combine the 1 and the negative 1 half. This is equal to half, and we replace it with 2ab. Now we have a perfect square, and we can simplify this expression to x cubed plus 1 over 4x cubed squared. This algebraic trick allows us to solve the integral. Recall that length was equal to the integral from 1 to 2 of the square root of 1 plus x cubed minus 1 over 4x cubed squared dx. By the calculation we did on the previous slide, this is equal to the integral from 1 to 2, the square root of x cubed plus 1 over 4x cubed squared. Now, we are taking the square root of a quantity squared. And this is a tricky matter. And I want you to slow down right now, because your instinct may be to cancel the square root and the square. And this is true for a lot of numbers. 2 squared is equal to 4, the square root of 4 is 2. But it's not true for every number. Take, for example, negative 1. Negative 1 squared is 1, and the square root of 1 is 1. It turns out that you can only take the square root of a quantity squared and get the original quantity back if the original number was itself positive. If it was negative, then you get the positive value of equal magnitude. So when we're trying to simplify this, we need to check that x cubed plus 1 over 4x cubed is positive. So we're restricting ourselves to the interval from 1 to 2. On that interval, x cubed is positive, and 1 over 4 x cubed is also positive. So in this case, we have no problem simplifying the expression and canceling the square root and the square. At which point we can simply use the power rule to take the antiderivative. We get x to the 4th over 4 minus 1 over 8x squared, evaluated from 1 to 2. We plug in the numbers and simplify algebraically, and it follows that the length of our curve is 123 over 32. Thank you for watching, and as always, you can reach me by commenting below or by emailing me at binger@math.ohio-state.edu. Have a good night.